All right, in this next video, I'm going to show you how to construct a confidence interval when we're trying to estimate a population mean. Now, we have two different scenarios, one where we know the population standard deviation and another where we don't know the population standard deviation. And when that's the case, we kind of run into a bind. So we're going to start with something pretty straightforward, and it's going to look really familiar to what we did with proportions and sampling distributions. So we're going to start off with this assumption that we know the population standard deviation. And we're going to do the same thing that we did in the last two sections. We've got some conditions that we need to check. Some of them are the exact same conditions that we checked in the last chapter, in the last section, and then the other relates back to what we did with sampling distributions. We're going to determine the critical values for finding a confidence interval. We're going to construct and interpret the interval using formulas and using technology, and we'll also be able to determine the sample size required to obtain a certain confidence interval. So we're going to start with the same sort of formula that we used in the last section. When we draw a simple random sample of size n from a population having an unknown mean, and in this case, like I said, we're going to start off with this assumption that we do know the population standard deviation. Now, in practice, that's really not possible to know the population standard deviation without knowing the population mean. Because if you think about it, the way we compute a standard deviation is by figuring out how far each of the values in the population is away from their mean. So if I don't know the mean, I can't exactly calculate the standard deviation. But we're going to start here with this known standard deviation and then just move slowly into the next situation, next class. So if we know the standard deviation of the population, we can determine a confidence interval using the same process that we did before. So again, I do want to just reiterate, whenever you're constructing a confidence interval, you always want to make sure that you include the confidence level. The statistic now, if I'm estimating a population mean, the statistic or the point estimator that I use to do that is not p hat anymore, it's x bar. Now the critical value, assuming I'm still using a normal distribution, so I will have to ensure that my normal condition is met, the critical value will again be a z-score. And it's going to be determined the same way that we did for population proportions. And then the standard deviation of the statistic, we'll think back to what we did with sampling distributions. How did we find the standard deviation of x bar? And if you remember, it was simply sigma over the square root of n. And so that's our formula for computing a confidence interval to estimate a population mean. And that's, again, it's only when we actually know the population standard deviation, which in practice is not something that happens very, very often. And this interval will be exact when the population distribution is normal. It's going to be approximately correct if our value of our sample size is more than 30. And then we'll also see what happens if neither one of those criteria are met, but we have data. If I wanted to use my calculator, I'm just going to show you, if you go to the same menu as we did with proportions, we go to Stat, and then scoot over to Tests. And this is where it kind of frustrates me about your calculator that it's not consistent in the way it names things. So you'll see pretty much any time that we're dealing with a proportion, you'll see the word prop. So the first couple of options you see are tests. These are all tests of significance. If you scroll down a little further, you'll start to see all the commands to calculate your confidence intervals. And you'll see, sometimes you see the word prop and sometimes you don't. If you don't see the word prop, then we're dealing with a mean. And you'll see that there are z intervals and there are t intervals. We're going to be working with a z interval today because we are going to stick with the normal distribution. But next class, I'm going to teach you about another distribution that we use to estimate a population mean when the standard deviation is not known. So again, on your calculator, this is considered a one sample z interval. You could also, to be consistent, say it's a one mean z interval, just to remind yourself. What's important here is that we're indicating that we're dealing with one sample, and there will be a time, again, when we are going to be comparing two populations and therefore need to take two samples. So for right now, we just want to reiterate that we're taking one sample from one population, we're calculating a mean, and we're computing an interval that involves the z, which that's our clue that we're using normal distribution procedures to calculate the interval. And so those are the primary things that you have to include. I'm going to write this down when I'm using technology, when I'm using my calculator command to calculate my interval. Otherwise, I'll just show my work, and then I don't care what this statement is. So if I show my work, I don't have to name the interval. But what the AP exam rubric requires is that you either state your procedures by stating the method or by stating the formula. So you just want to make sure that you do one or the other. Okay, our conditions for inference about a mean. Remember, we've already been working with these two conditions. If we're sampling without replacement, we need to ensure that our population is at least 10 times our sample size. And when we're dealing with means, we either need to have it stated in the problem that our population is normal. And remember, when you're stating the condition, don't just write normal and then write a check mark, or write it is normal and put a check mark. Make sure you're referencing the population. The population is normal. Then you can put a check mark that that condition is met. If it doesn't state in the problem that the population is normal, then we need to have a large sample size. And so you're going to write n equals whatever and then determine if it's greater than or equal to 30. And again, make sure that you're labeling it as your sample size. So for example, if I'm taking a sample of 40 and I'm checking conditions, I'm not just going to write 40 is greater than 30 and put a check mark. That doesn't indicate that I'm checking a condition. It's just telling me that 40 is greater than 30. So to justify that you're checking a condition, make sure you associate it with the sample size. And then finally, we said that the new condition for inference that we need to make sure that we acknowledge is that the data come either from a random sample or a randomized experiment. All right. The other thing that we can do with means that we can't do with proportions, if it doesn't tell us in about the population being normal and it gives us an n value that's less than 30, if we have the data, so if data is given, even so, let's say we have a sample of 20, but I have all the data. So obviously it's not more than 30. The central limit theorem isn't going to apply. And if I don't know anything about the population, if I'm given the data, then I can construct a graph. And I would recommend that you construct a normal probability plot because it's a lot faster to draw on your paper. And whatever graph you calculate or whatever graph you construct on your calculator, if you're referring to it, you need to make sure you put it on the paper too. So if the distribution of the population isn't given and your sample is less than 30, you must plot the data if it's given to you. If you're not given the data, then you're sort of stuck. And so you can proceed with caution, or you can simply say, you know, we can't proceed because the distribution isn't, the sampling distribution isn't normal. And I'll go back over how to do a normal probability plot. If you hit second y equals, that takes you to all your plots. And a normal probability plot is going to be the last one you see so this is just a regular scatter plot. This is what we call a time plot where all the points are connected. The third one is a histogram. Then we've got our two box and whisker plots. Now remember, a box plot will show you symmetry, but it's not going to be enough to justify a normal distribution because you can't see the bell shape. So if you're trying to show something's normal with a plot, then you either want to construct a histogram or a normal probability plot, which is that very last plot. And just hit zoom 9. And if the data is linearized, then that tells you that the sample, not the sampling distribution, but the sample is approximately normal. And if you sketch it on your paper and say the sample is approximately normal, you can actually continue. All right, so let's take a look at an example. In number 1, it says a manufacturer of a pharmaceutical product analyzes a specimen from each batch of a product to verify the concentration of the active ingredient. The chemical analysis is not perfectly precise, and repeated measurements follow a normal distribution quite closely. So we're told it's normal. We're told the population is normal. Let me clarify. The analysis procedure has no bias, so the mean of the population of all the measurements is going to be the true concentration in the specimen. The standard deviation of this distribution is known to be 0.0068 grams. Notice one of the things that I just want to make sure that we point out is when we are estimating population means, you need to make sure that you include units now. We didn't need to worry about that with proportions because it was just a percentage, but now with means and standard deviations, you do need to include the units along with the context of the problem. So anyway, the laboratory analyzes each specimen 3 times and then reports the mean results. So in letter A, it says these analyses of one specimen give the concentrations. You're given 3 values, and you're asked to construct a 99% confidence interval for the true concentration, mu, of the active ingredient. So I've already entered my values into a list. Now, in this case, I'm told that the population is normal, so if I go ahead and check all my conditions, I believe we can, if we assume that the 3 measures are a simple random sample from the population, then it's appropriate to continue. We're not sampling without replacement because this is an infinite population, because I can continue measuring over and over and over again. You can either state that it's an infinite population, or you can simply say assume that the population is more than 10 times 3 or 30 measures. And obviously we can measure this thing a lot more than 30 times. So either way, you're covered there. And then the last thing we want to check is the normal condition. And so here we would simply say the population is stated to be normal. So all our conditions are met. So if I'm going to do a 99% confidence interval, I'm going to write that first, 99% confidence interval. I already know my z-score for our confidence interval. That's going to be my 2.7576. And if we forget, I can just go to my inverse normal command. And if it's 99% on the inside, then I know it's going to be 1% in the tails together. So in one tail, I'm going to have 0.5%. And so it's 2.576 as my z-score. I need my estimate, though, and it's not given to me in the problem, but because I have the 3 measures, I've put those values into a list. So if I simply do my one variable statistics command with list 1, I get an X bar of 0.8404. Actually, let me scoot this over a little bit. So my estimate is 0.8404 plus or minus 2.576. And I need to also multiply that by my standard deviation of the statistic. I am given sigma in this case. It is 0.0068, and I'm going to divide that by the square root of my sample size, which in this case is 3. So that is the formula for computing my interval. To actually calculate it, I'm going to do the lower bound first, 0.8404. Oops. And I'm going to do my subtraction first, 2.576. And I'm going to multiply that by my standard error, or my standard deviation. And in this case, it is a standard deviation of my statistic because I'm using the population parameter. So this is not a standard error. It is the standard deviation of X bar. Okay, so this is going to be my lower bound, 0.8303. And then I'm just going to hit second enter, or second entry, and I'm going to change my subtraction to an addition symbol. And then I can compute my upper bound, 0.8505. And again, because this represents the mean of a population, I want to make sure I include units, and that would be grams per liter. Okay. And then if I were to interpret this, I'm going to interpret it the same way I did with population proportions. We can be 99% confident that the true concentration for the specimen is between 0.8303 and 0.8505 grams per liter. Okay. In part B, It says, suppose that a single measurement gave an x value of 0.8404. Determine the 99% confidence interval based on this single measurement. So essentially, it's the same formula. It's going to be the 0.8404 plus or minus the 2.576 times the standard deviation, but I'm dividing by the square root of 1. And so if you actually do the computation, I'm just going to go ahead and do it right here, you end up with 0.8229 to 0.8579. And when I compare those two values, I actually find that this is wider than the confidence interval with a sample of 4. Or a sample of 3, I'm sorry. So that should make sense. As we increase our sample size, we would expect the width of our interval to decrease. So the larger the sample, the smaller the spread, and that would affect my interval. I also want to show you how you can compute the confidence interval using technology. And again, it's the same thing. So I've got my data in list 1. So if I go to stat and then I scoot over to tests, again, I want to scoot down to my interval commands. And notice that with the 1 samples, it doesn't give me a 1 sample option. I mean, I have the 1 proportion z interval. But if I just want to compute a 1 sample confidence interval for means using my z's, the command on my calculator is simply z interval. And if I choose this, I have 2 options for input. It says I can use data or statistics. So in this case, I'm not told what x bar is. I'm given the data. So in this case, I would choose data as my input. And then notice it asks what the standard deviation of the population is. And in this case, I'm going to put 0.0068. And then the list is me telling the calculator where the data is. Well, I put the data in list 1. If my problem gave me my sample mean, so if it told me what x bar was, I would use my statistics menu instead. So I'd scroll over to the right where it talks about the input. I'm not entering in a frequency list, so I'm going to keep the frequency at 1, and then the confidence level in this case is 0.99. Okay, and so I'm going to go ahead to calculate, and you can see that the confidence interval that the calculator reports is essentially the same one that I computed by hand. So let me just show you what the command looks like if I'm entering in like an x bar. So if the problem reports an x bar, I'm still going to choose just the plain old z interval on the calculator. But just remember, on your paper, you still have to write that it's a 1 sample z interval. And I would just indicate also that it's for means. So if I were to have an x bar value, you'll see that it changes what's being asked of you. We'd keep the sigma the same because that's what's given to us in the problem. We'd write down the x bar that is given to us in the problem and the sample size and just enter in the information that's given to us. Okay, let's talk about how confidence intervals behave. So the confidence interval, x bar plus or minus z star times the standard deviation over the square root of n for the mean of a normal population, indicates several important properties that are shared by all confidence intervals. So this would be true even for proportions. We definitely want to have high confidence, but we also want to have a small margin of error. So high confidence says that our method almost always gives correct answers, and a small margin of error indicates that we've sort of pinned down the parameter quite precisely. If you remember the Garfield example, the comic strip that I showed you where Garfield was watching the Weather Channel and the guy said it's going to be between negative 40 degrees and 200 degrees. Well, sure, I can be 100% confident if I increase the size of my interval, but that doesn't really help me estimate a population parameter. So we want to keep our confidence high and the margin of error small. Sometimes the margin of error we use a small m instead of ME. in terms of our notation. But if you think about the three factors that affect our margin of error, we've got our z-score, which is our confidence level. I mean, that is associated with our confidence level. We have our standard deviation of the population, which we usually can't control and almost always don't know. And we have our sample size. So if you think about things that are going to make my margin of error small, having a small z-score is going to, so if I want to decrease the margin of error, okay, if I want to decrease the margin of error, having a small z would enable me to do that. If I have a small z, that means I have to decrease my confidence. Okay. I could also decrease my standard deviation of the population, which again isn't something that we can usually do, or I can increase my sample. Okay, so there are three things that we can do to decrease our margin of error. If I want to make my margin of error small, if I want to decrease the width of my interval, I can decrease my confidence level. I can decrease the standard deviation of the population, which honestly isn't always possible, or I could increase my sample size. And so what we usually do, since this is the one thing that we can easily control without having to sacrifice our confidence level, that's typically what we do, is we increase our sample size. So let's talk about an example where we have a fixed margin of error and a fixed confidence level. This is just another shot of what I just mentioned. So our margin of error is going to decrease as z gets smaller, but that's only going to happen if we decrease our confidence level, so there's a trade-off. Or our standard deviation gets lower, or n gets larger, increasing our sample size. We'll maintain our confidence level and decrease our margin of error. All right, so let's take a look at that last example. If I want to create a sample size, or if I want to collect a sample where I have a fixed margin of error and a fixed confidence level, I'm just going to use that second side to my confidence interval, the z times my standard deviation, sigma over the square root of n. And I'm basically saying, just like we did with the proportion, that the margin of error that I have, this quantity has to be smaller than that value. This time, though, my margin of error is not going to be a percentage, because remember, we're dealing with means. So my margin of error is not going to be a percentage. So in number 2, it says management asks a laboratory in the previous example to produce results accurate to within, I think your paper just didn't actually show up on my slide. So within a margin of error of 0.005 and a confidence level of 0.95. We already know with a confidence level of 0.95, that gives us a z-score of 1.96. So that's fixed. My margin of error is fixed. Actually, let me just go ahead and write this here. We were given the standard deviation in the problem to be 0.0068. So all I need to do is solve for n. So again, my margin of error has to be greater than or equal to my z-score times sigma over the square root of n. I know the margin of error is capped at 0.005. I know my z-score is 1.96. I was given the standard deviation of 0.0068. And I'm essentially then dividing by the square root of n. And I can just put the square root of n under the entire quantity. This is just a proportion that I need to solve. So if I multiply both sides by the square root of n and divide by my margin of error, I get 1.96 times 0.0068, and that is all under 0.005. And again, to solve for n, I've got to square both sides. And so on my calculator, if I go to my home screen, I'm going to put in parentheses 1.96 times 0.0068. I'm going to divide that by 0.005. That's that's my margin of error. And then I'm going to square both sides. And I get 7.105. So n must be greater than 7.105. And even though that value, if I were to round it, would round to 7, I always, always, always want to round up. And so this would actually round up to 8. And so I would want to measure it 8 times. My smartboard's acting weird. Okay, and then there's one more problem that's very similar to this. And number 3, the possible scores for a certain standardized test range from 0 to 500. Suppose that the standard deviation for this test is 120 points. So I'm going to take my 120 as my standard deviation. You're trying to determine a mean score for all students in your school. How large a sample of students would you need to be able to estimate the mean within, oh wait, it doesn't, I don't know why my, the margin of error isn't showing up here. So we said plus or minus 50 points. That's going to be my margin of error. And we know our confidence level is 95% again. Okay, so that gives us a z-star of 1.96. So when I set this up, I know that 50 is going to be greater than or equal to 1.96 times my standard deviation of 120. All of that's going to be over the square root of n. And when I solve for the square root of n, and I square both sides, you should get that n is greater than or equal to 22.13. So I'd need a sample of 23 students. Okay. All right. So at this time, I'd like you to go ahead and get the homework. If there's any time left in class, you can go ahead and get started. Otherwise, obviously, you can finish it up for homework. And I will post this video to Blackboard. If you have any questions, you can certainly watch it again. Have a great day, and I will be back tomorrow.